Thank you for joining us today for the ISTRACT South African Regional Group Technical Talk 2 for the year. Today we are joined by Julian Birbeck, who will be presenting on the Elizabeth line and engineering parts that make the line unique. Julian is a chartered structural engineer with over 25 years worth of experience. Julian has worked on landmark structures across diverse sectors, and over the past decade he has specialized in facades and secondary structures. He is passionate about promoting structural engineering beyond its traditional boundaries, and I've been fortunate enough to work alongside Julian at AtkinsRéalis. So today this session is recorded, and we will allow some time at the end for a question and answer session. So without further ado, Julian, over to you.
Great. Thank you, Fiona, for that introduction. And welcome everybody to this lunchtime talk regarding the Elizabeth line. I'm aiming to talk for about 40-45 minutes. So there will be time for questions at the end. So yes, the Elizabeth line, engineering the parts that make the line unique. Talk's going to be a little bit like a journey on the Elizabeth line, in that we'll start at street level. We'll survey the scene, set things in context, and then I'll unpack a little bit more about my role and AtkinsRéalis' role within the grander scheme of things on the design and construction of the line. I'll then focus in the main body of technical detail will be around the platform edge screen, both the design, the testing and prototyping, and also some of the site issues that we had. So that's going to be our sort of deep dive into technical detail, and then we'll resurface on the other side. I'll mention briefly some of the other tasks we had as part of our role on the Elizabeth line, and then finish up with some reflections. So we'll start off high level, we'll delve into some structural detail, and then we'll come out the other side and reflect on it. So without further ado, I'm conscious that we've got a mixed audience today. Some of you will be familiar with London and the London Transport Network. Some of you are 5,000 miles away, might have visited London, might never have visited London. So firstly, I'll explain what the Elizabeth line is to the uninitiated. So Elizabeth line was originally known by the working title Crossrail, for which it was worked under for most of the duration of its design and construction. And Crossrail is quite a good name because it does what it says. The Elizabeth line is a line linking across London from east to west. So here's a map of the overall route. So it reaches out to suburbs and commuter towns in the east and west. Those sections are running on existing surface rail, which is the purple color on this diagram. And then in the center of town, the Elizabeth line ducts underground. There's 13 miles of subsurface route, almost entirely in new tunnels. So twin bore tunnels, that's approximately 26 miles of new tunnels were constructed. Key to mention that it, as an idea, was around for a very long time. First conceived in 1941, went quiet for a while, resurfaced as an idea in the 80s, the 90s, was finally given royal assent, that's the UK Parliament approval in 2008, and then that initiated the design and construction. Originally programmed to be a 10-year delivery program, was finally opened in 2022. Looking at this, realised Elizabeth line is a very apt title because it's actually taken the reign of Queen Elizabeth II, plus a little bit more at the beginning, to go from initial idea through to final completion. So zooming in on that central section of the line, the tunneled section of the line, there's these 10 stations, and this little org chart here in the center shows how AtkinsRéalis, or Atkins as we are then branded, fitted into the picture. So we were working as part of the line-wide design team, whose task it was to create the common identity, the common visual identity, the common customer experience through these 10 stations in the central London portion of the line. And just to zoom in on that a little bit further, so out of those 10 stations, 5 of them were what we termed mined stations. And you'll see in a second on the next slide exactly what I mean by mined. But this slide also shows us a very high level, the station diagram. The stations are quite long, typically 200, 250 meters long of platforms, with a separate ticket hall at each end. So the main focus of my technical talk today will be on these mined stations. And when I say mined, this is what we mean by mined. London is geologically underlain by London clay, so the majority of the tunnels were being constructed through London clay. The running tunnels are constructed a tunnel boring machine, TBM. The running tunnels themselves have precast concrete tunnel lining segments, but the stations where the diameter increases for the platform tunnels, and then there's a network of interconnecting cross tunnels and concourse tunnels, they're actually literally just dug out from the main running tunnel bore. As you're excavating through London clay, it has some temporary load-bearing capabilities, so that permits the use of this sprayed concrete lining. So the structure of the station tunnels is fiber reinforced concrete sprayed onto the surface of the London clay in a series of layers, and that gives quite a distinct appearance in its raw condition. So I'd ask you just to memorize this photo for a second, because you'll see as we go forward that this was key to the visual concept that was then developed for the appearance of the mined stations. So just to take a moment to explain a little bit more about the strategy and how the line-wide design fits into the overall design of the network. So each station, each ticket hall is in its own position within the London streets. So was designed by a different architect, a different design team to respond to that urban context. But as the passenger enters the station, goes into the ticket hall, descends escalators down to platform level, the overall idea is that they will then leave the street identity behind and then become enveloped within the line-wide identity of the underground portion of the line. And it was this line-wide identity that was the remit of the line-wide design team. So I'll now spend a few slides just to unpack that a little bit more. So the line-wide design team also went by the name of the common components package with the catchy title C100. So on a massive project like the Elizabeth line, each contract had its own C prefix. For example, Farringdon Station was C435. C100 intentionally, had a round number at the top of the sequence to communicate that the line-wide design had an overarching role to bring all the other contract packages and station design packages together. So the design team comprised 4 organizations: Atkins Realis as engineers, structural and MEP engineers, Grimshaw as the architects, Equation, a lighting design consultancy, and Maynard Industrial Design. Within the common components package, there was a shopping list of about 10 or 11 different elements, ranging from the kind of elements you might expect to be in a common components package, everything from sort of signage to balustrades to seating to lighting, with a clear intent of coming up with unique, distinct industrial designs for each of these that then will be repeated across the network in the centre of London. In addition to that shopping list of items. The common components package were responsible for conceiving and delivering the overall architectural vision for the tunneled stations. And here you have that concept summarized here, both in a concept drawing and a CGI. And if you cast your mind back to that slide a few minutes ago with the sprayed concrete lining, you can see a couple of things. Firstly, that sprayed concrete lining as struck is quite irregular. So quite early on, it was identified that would need some sort of tunnel cladding. The system that was chosen was GRC, glass fiber reinforced concrete. Don't know if you're familiar. So that's basically concrete, fine aggregate cement reinforced with glass fibers. It can either be sprayed or poured. It's typically sort of 15 to 20 mil thick, so it forms some quite thin, lightweight but durable concrete panels. So the intent was to use this throughout the platform tunnels. In doing so, these concrete panels create a panelization pattern. You're running down the axis of each tunnel, and then where the tunnels intersect, significantly, the sprayed concrete lining naturally gives you a radius in your tunnel lining structure, and that was expressed through into the architecture, which gives you many advantages. It eases passenger flow, it eases sight lines, and it creates this very distinct pattern and form where tunnels intersect. The panelization sort of wraps around these radius intersections and gives you a very interesting pattern, curved pattern as the cladding panels intersect around the corner. And then carrying that vision through to the platform tunnels. Design team knew from the outset these tunnels are unlike anything else on the London Transport network. They're twice the length, up to a quarter of a kilometre long. The intent was to maximise the visual impact, but to also keep it uncluttered. So to use the GRC cladding panels right up to the apex of the tunnel, and to gather as many functions as possible onto the platform edge screen wall. So this black wall you see on the left-hand side of that image, that is both providing a screen to the trains, but it's also housing advertising, it's housing customer information systems, it's housing signage, it's housing public address. The lighting, the whole lighting from the platform is being lit from that light band you see running down the platform edge screen and then being reflected off the GRC panels. And it even conceals a ventilation as well. So in order to keep the platform space clear and uncluttered, both spatially and visually, the platform edge screen was required to work very hard and perform a number of distinct functions. And just to emphasize the whole philosophy of common components, the pipe analogy, I guess, is quite obvious from the intersection of the tunnels. But to explain that our colleagues at Grimshaw, from the outset, worked to rationalize. So very early on in the design, they engaged with the civil engineering teams responsible for the design of the station tunnels. And in doing so, they were able to rationalize what started off as, I believe, over 40 different tunnel diameters across the 5 stations we referred to in the centre of London. They managed to get that down to 9, and doing so saved a heap of complexity and managed to maximize standardization and repetition. And what that meant is for the key details, for example, that very distinctive intersection between the cladding on tunnels at 90 degrees, where the cladding wraps around that radiused intersection. They only had to solve that problem once for a typical intersection between a platform and a cross tunnel, and then that solution to the problem, that coordinated design, could then be given as a common component, as a sort of plug and play reference design to each of the station design teams to then fit into their particular station layout. So that's the common components approach, and that is exactly what was applied to the platform edge screen, which is what I'm going to describe next in a little bit more detail. So excuse me 1 second. Let's take a... So yes, the platform edge screen, or PES, as it was commonly referred to. At first sight, yes, it's obvious from the title. Yes, that's a screen on the edge of the platform. Shown on the left-hand side in this little architectural cutaway. And on the right-hand side, you have a 3D model of the platform edge screen undressed, as it were, showing the structure underneath. And it's that structure that I'm going to describe in a little bit more detail. But firstly, what is a platform edge screen? Which is might seem an obvious question, but it's a question worth answering because it's a little bit more than you might think. So obviously, it has a function to stop people accidentally or deliberately going off the edge of the platform. But you could do that with something at balustrade height, which is what's commonly termed platform edge doors. The middle approach is an extension of that that's used on many metro systems around the world, where you take those cantilever structure the doors and take it up above head height. And in doing so, you're providing additional screening effects, shielding the passengers on the platform from some of the acoustics and some of the air buffeting from the arrival of the train. But a platform edge screen, by definition, is actually an element that seals from platform level up to ceiling level, and it is effectively sealing off the rail running environment from the platform, which has a couple of really significant advantages. You can appreciate in doing so, you're avoiding pushing all the air, the piston effect of the train through the stations, which means that firstly, the tunnel ventilation system can be designed for much faster movements of air than would otherwise be tolerable. Now, I'm reliably told by tunnel ventilation specialists that the use of platform edge screens for the central section of the Elizabeth line actually removed the need for 6 further ventilation shafts, which otherwise would have been required in the centre of London. So that's massive in itself. In addition, by sealing off that environment, you're just easing the maintenance and durability of the station, in that you're not pushing all that dirty air for the brake dust and rail filings into the station every time a train moves. So the platform edge screen, as well as having the safety function, has a key ventilation and environmental function as well. So coming back to our diagram of the platform edge screen structure, you see that item number 7 is actually the platform screen doors. So they are procured by via a specialist contractor, and to use a facade terminology, they're effectively a form of unitized construction. So they are pre-glazed on a lightweight frame with all the doors and moving parts, factory assembled. They're actually delivered by train and installed, as one of the final stages of completion of the platform edge screen. So they could merit a whole talk in themselves, but my focus today isn't on those. It's on the actual framework that you see on the right-hand side, the platform edge screen structure. So on that, I'm going to focus in on 6 technical challenges, as you see here: the setting out, the structural diagram, construction sequence, tolerances, earthing and bonding, and durability. So the setting out of the platform edge screen. So bearing in mind everything that we've been saying about common repeating components, the philosophy of the platform edge screen was exactly that although you've got up to 250 meters per platform, which on the right-hand side, just for reference, is overlain on the London skyline, or a 2018 version of the London skyline, at which point it would have been, if you stood the platform edge screen on its end for one platform, would have actually been the tallest structure in the City of London. Not anymore, but beside the point. Sufficient to say it's a very long structure, but it's built out of a small repeating module. So the basic structural module between connections into the tunnel lining is 3 meters. There's a Vierendeel spanning element, which is sort of on half that module. So typically on a 1.5 meter module for the framing of that Vierendeel. And then the posts that prop the PES structure down onto platform level are actually off module. The reason for that being is that their position is dictated by the train doors, and the train doors are subject to 2 variables that are separate from the structural model. First is the stopping point of the train, and the secondly is the type of rolling stock, which wasn't known when we started designing the PES and could still change in the future. So as such, the posts that prop the PES structure are designed so that they can prop at any point along the bottom chord of that Vierendeel truss, and that Vierendeel truss is designed to accommodate a range of spans from about 6 meters up to about 9 or 10 meters, depending on the configuration of posts. Another point to note is that you can see on that elevation movement joints. So yeah, if the whole structure's 250 meters long, need for movement joints for expansion. These are typically at either 15 or 18 meter centers as you go along the truss structure. So the structural diagram, again, more complicated than you might first think, because we had to adapt between different conditions within the construction of the stations. So when the PES was first installed, the top elements were constructed to hang, to be suspended, as that left-hand diagram there. That was to leave clear space for the works underneath, notably the track installation. And then once the track installation was complete, there was a strong design not to leave the PES structure hanging in the permanent condition with all the additional sort of hazards inspection associated with concrete anchors in permanent tension. So once the track installation was complete, props were installed, bolts released into slotted holes at the top, and the structural diagram then becomes this propped configuration. Important to note that propped is still articulated at the top to allow for long-term movements in the tunnel crown, tunnel squat, as it's termed, when the vertical dimension of the tunnel can reduce over time. So that was a structure diagram, and just to give us a couple of snapshots of how that looked in practice. So in terms of the construction sequence, the first step was to install the connections into the sprayed concrete lining at high level and at the sort of 2 o'clock position. They were installed first along the whole length of each platform in order to ensure that they were completely line and level. As we'll see in a second, the design of those connections was key to being able to take out the large tolerance you have in the sprayed concrete lining. Next, the galvanized steel PES frame would be installed in the hanging condition. And then once the track was installed through the station and the other fit out works are more advanced, the props would be installed. On the right hand side, as you can see, the top connections released and the PES transitions to its propped configuration. So tolerances. A key feature of the spray concrete lining is by its nature, it creates a large tolerance envelope up to 100 mil. The surface can vary, and we needed to, as a structural design team, come up with a solution that would accommodate that level of tolerance. And what was adopted, you see as right-hand sketch, was to fix into the tunnel lining using self-tapping concrete anchors. In particular, we focused design around one particular proprietary type, large diameter than those which are commonly available. So an M20 self-tapping concrete anchor with a threaded stud portion on the protruding element, and that threaded portion gives you the flexibility to set your steelwork at the right level. So you see in this diagram here that you've got the the fabricated steelwork, and then you've got a zone of grout between that steelwork and the spray concrete lining, and it's that grout that takes up the tolerance and, in effect, inverted commas, seals the pez against the sprayed concrete lining. So we'll come back to those self-tapping anchors in a few slides because they were subject to some pre-construction testing. But I will now just take a moment to talk about packaging. So in a station tunnel, you've got the tracks operated by the rail operator, TfL, and then you've got the station environment operated and maintained by London Underground. And at first sight, it would appear the pez is a natural barrier between those two systems and those two zones of responsibility. So that left-hand diagram would at first sight seem the most logical way to divide up the platform tunnel, but there was a need to introduce a substantial ventilation duct at high level. And you can appreciate, having seen the architectural visualizations, that having some talking great duct above your head at platform level would have completely changed the whole visual quality and environment of the platform. So that was dismissed. And the opportunity was identified, having looked at the tunneling cross section, to use the clear space above the track and above the overhead line equipment for the ventilation plenum, which in cross section looks like a very neat and rational idea. In practice, that created a few more challenges than you might think, because that duct and plenum was part of the station systems, used to be operated by London Transport personnel, and they are not used to overhead line equipment with 12,000 volts running through it. The London Underground runs on direct current third rail system that has about 700 volts. So their operatives, their unions, were very, very vociferous about this new scenario they're presented with, working in proximity to such high voltages. And as a result, it was agreed that that duct would be designed in such a way so anyone reaching into it to maintain it would not be able to touch or see anything metallic. So as such, as designers, we were required to design a series of precast concrete planks installed in a 750 module that created the soffit of that extract plenum above the tracks. So that's one way in which the challenges of dealing with railway voltages underground affected the pez design. Another way was the design of earthing and bonding. Bear me a second. So earthing and bonding may be a little bit opaque to us as structural engineers, not something we normally have to deal with. But the issue is when you're on a electric train, particularly one that runs on overhead line equipment of high voltage, you're actually part of an electric circuit. The whole train, the earth of the whole train, is floating relative to its environment. This is to do with how the current flows back through the rails, and there needs a certain voltage to drive that. So if you're on an electric train, you can be up to 50 volts higher voltage potential than the surrounding environment, which is not a problem when you're on the train because you can't touch anything. But when you get off the train, the platform needs to be designed so that you cannot touch anything that's at the station earth voltage. So you appreciate what that means for the pez design on this left-hand diagram, sorry, is that the structure of the platform screen doors themselves, the metallic structure, needed to be electrically isolated from both the platform and the upper portion of the pez frame. The platform level just bolted into concrete, and there was some non-conductive rebar in the platform edge. But at the head of the PES frame, that meant that we needed as structural designers to find an electrical isolator that was up to the job structurally, to provide that isolation within the steel frame. If that wasn't complicated enough, London, or actually throughout the UK, subsurface rail has been subject to very stringent fire regulations since the King's Cross disaster of 1988. So the regulations that were brought in after that were very onerous and prescriptive, and dictate that anything, in inverted commas, used in the construction of a wall needs to be of inverted commas, a limited combustibility, which is in effect non-combustible. It's class A2 S1D0 to BSEN 13501, if you're familiar with that. But that was a requirement for these isolators, and as such, that presented a challenge. Initially, we wanted to use phenolic GRP, a very high-performing electrical isolator, but also very high-performing in terms of its resistance to fire. It's used on space capsules, but because it works by charring, it couldn't pass the non-combustibility test. So we were forced to look for an inert mineral option to achieve this electrical isolation. There was various forms of engineered ceramic considered. In the end, we landed on a product, mica glass, which is actually what it says. So it's fragments of mica embedded in glass to reinforce it. This was available in proprietary isolators, affectionately known as by the team as hand grenades, which you can see here. It's this double female threaded isolator with bolts coming in top and bottom, but no direct conductive path from the top structure to the bottom structure. So we'll be seeing a little bit more of those in a second. We'll talk about pre-contract testing. Finally, a note on durability. So you can appreciate, given the location and the configuration of the PES, it was not conceivable that it could be easily replaced, or at least the supporting structure of the PES could not be replaced within the service life of the station. So it needs to be designed as a civil engineering structure with a 120-year design life. So you've got corrosion protection to consider, bearing in mind that we've got across 5 stations up to 2.5 kilometers of this structural frame. The idea of constructing it in stainless steel received significant pushback from the costing point of view. So the design team took it away, and it concluded that an enhanced galvanizing spec would be sufficient within the environment. So as such, the steelwork was galvanized to a minimum of 140 microns. As you can see in this photo here, gives it a very sort of bright finish when it's first installed. But then another aspect of durability, which is maybe a little less obvious, but when you start to think about it, becomes apparent. So bearing in mind what I was saying earlier about the PES sealing the station environment from the rail environment, means that it's picking up a significant wind load with every train movement. And although there's some exceptional wind loads, which actually created the sort of design ultimate wind case, for most train movements, you are at 50-60% of the maximum design wind pressure. And when it was factored in that trains could run every 3 minutes apart, as every intent for like a 24-hour timetable in the future, you're up to over 20 million stress cycles within a 120-year design life, which takes you into fatigue territory. So the steelwork connections, which were the design team literally developed all of those as part of this common components approach. We designed all the way through to completing the steel connections, and those steel connections had to be designed with fatigue in mind. So those are the 6 technical challenges. And now just a couple of slides just highlighting some of the pre-construction testing that was undertaken. Noteworthy that the testing was actually undertaken under the remit of the C100 Common Components package. So the PES design was in effect sort of pre-tested before it was handed across to the station design teams, which differs to what's often seen, particularly in the facade sector, as a procurement strategy when all the sort of testing is pushed into the supply chain. C100 we did the opposite, and the C100 team took on the role of scoping, witnessing, and interpreting pre-construction tests. So they fell into two main categories. So the testing of the electrical isolators, these mica glass isolators, quite novel within this use. So they were subject to extensive testing regime, which modelled that cyclical effect I mentioned of the train movements. So I think our test rigs went up to about 2 million cycles. We comparatively did mica glass with some other engineered ceramics. And as you can see from that photo at the bottom, some of them didn't make the grade. So the pre-construction testing was instrumental in allowing the team to focus in on mica glass as our solution. And then the other key area of testing was the proprietary threaded anchors themselves. So the Excalibur bolts, they had some data in terms of conventional and reinforced concrete, but we were conscious that because of the unique process of the spray concrete lining, there was a need to gather test data for their capacity in spray concrete lining. So at Vinci's test center, a number of sprayed concrete lining panels were constructed using the same methodology that would be used in the tunnels. And then into these panels were drilled a whole array of Excalibur bolts, which were then subject to a series of destructive, tensile, and shear tests. And then our colleagues at Imperial College then did that test and then took the results, did the necessary statistical analysis in order to determine ultimate characteristic design values that could be used for those anchors in the spray concrete lining with the appropriate margin of safety that's required by structural Eurocodes. Site issues. Actually, this section is quite short, just one slide short. So across 5 stations, you can appreciate there was numerous issues in terms of local issues of workmanship and setting out and coordination, but I focused in just on one particular site issue of interest and of note related to, again, the electrical isolators, as in the way when you use anything novel and innovative on a construction site, unforeseens are going to manifest. So we did the off-site testing when I think it was Tottenham Court Road Station was one of the first to install these. When they started to torque them up, they noticed that a number of them were cracking, as you can see in this photo here. And from a quick inspection, it became apparent that this was occurring where the two end plates were not parallel. You can appreciate about 30mm thick plate, quite substantial welding. We're getting some heat distortion in those end plates. As such, the surfaces between that you were trying to connect the isolator were not parallel. So as you torqued up the bolts, if those bolts weren't quite parallel, as you torque them up, you're introducing bending into those isolators, which was causing them to crack, a brittle failure. Some rather hasty rethinking by the design team, ingenious thinking by my colleagues. It was determined that with an insert, you could step down the diameter of the top bolt to take it from an M16 down to an M12. In doing so, you're then effectively making the top hole oversized to give you that angular tolerance through the 30mm thick plate. So there's enough clearance if the bolt is not quite straight that it can still pass through that hole. Neoprene washers top and bottom to take out a bit of the alignment. And in doing so, we were able to resolve this issue. We were able to come up with a configuration where the bolts could be torqued up, and even if they weren't 100% parallel, it wouldn't lead to a failure of the isolator. So there's always going to be something. The lesson learned is to, if you're specifying pre-construction tests, always to try and foresee the very worst, foreseeable conditions and try and make sure those are modeled in the test. As it was, our test group was fabricated, to slightly tighter tolerances than we actually ended up with, across the network on all the sites. So yeah, moving on. So we're starting to resurface now. I've been into the depths of the nuts and bolts and the technical details. So I was just going to touch upon some of the other engineering inputs that we had aside to the structural engineering of the PES. And I think these are interesting. It ranged from everything to checking the natural frequency on these left-hand side, what we call the totem signage. So if you saw in the early images, they are positioned down the main station concourse. They provide signage, they provide directional signage, and they also have an uplighter. So they're key to the lighting of the concourse. From the mock-up, off-site mock-up, there was a concern that people doing mischief might try to sort of set off the natural frequency, the oscillation of these. So we were asked by the architects to undertake a quick study to review the natural frequency and suggest some enhancements to the subframe of these to make sure that natural frequency was, above a suitable minimum, to avoid the risk that miscreants, I think we call them, people doing mischief, might suddenly discover that they could set these things wobbling. A similar vein, and I find it quite amusing that we even got to the point where we were asked to check bending moments on litter bins, but absolutely, why not? You're trying to make sure you're creating a robust, durable platform environment. Litter bins might be prone to misuse, abuse, either intentionally or unintentionally, people climbing them, putting weight on them. So we were asked to check by the Crossrail architects the bending moment capacity of litter bin, which was the first time I've been asked to do that in my career. But why not? It was entirely within the remit of the Common Components package to produce this set of components that were rigorously engineered and durable. So that leads me into the final section of a presentation, which is really just sort of reflect on what it all means. So, in case you're not already aware, October 2024, the line-wide design of the Elizabeth line won the Stirling Prize, which is the most prestigious architectural prize in the UK. In doing so, it sort of confounded some people's expectations, and also really sort of woke people up to really what is the definition and the scope of architecture, and just the idea that something like a metro system, subsurface tunnels, platforms, or as much architecture as a building or a tower. Absolutely right, but it was a real milestone that was sort of recognised at this highest level. The judges praised the uncluttered, the clean nature of the appearance of the station tunnels, and notably on this right-hand image, you can't actually see any of what I've been describing. This structural frame, all the complexity, all the electrical isolators, all the concrete panels, you can't see any of it. And well, first sight, we might get upset by that, can't see what we've done. But in my view, as a structural engineer, that's often what good looks like. If you get to the point where your intervention is so well executed that it's almost invisible, I think that is a good outcome in this case. So I entitled this talk at the beginning, Mind the Gap. And yes, please forgive me this. I know it's a bit of a, if you're familiar with the London Underground network, it's a bit of a cliche, it's a bit of a meme. We have throughout the network these spray painted warnings on the platform edge, and in some stations. It's even sort of barked out on the tannoy as a train comes in, mind the gap. But I thought I'd include this. Just, I think it's relevant in threefold. I mean, firstly, by designing a platform edge screen, we've removed that hazard of people falling off the platform edge. Secondly, in terms of all that the line-wide design and the common component design achieved, it transformed the environment of subsurface rail in London. So whereas previously you had all this visual noise and actual noise of sort of written warnings and audible warnings, being thrown at you as a passenger, you've created this well-designed environment where the hazards have gone away and the need for all the, the warning and the, screaming for your attention has gone. And the third reason I think is a bit more sort of philosophical, but it's almost the gap is like a metaphor that a project like Elizabeth Line comes along, and of course, as structural engineers, civil engineers, we get involved with with the meganewtons, with the heavy civils, the large forces that are associated with the design and construction of the tunnels. But what we did with the C100 Common Components package was take it a step further once the tunnels were complete to apply our structural engineering skill to those secondary elements that take are supported from that tunnel lining, but create the environment that the passengers, the customers actually see and interact with. So 4 thoughts just to finish up. So one, I think, as engineers, we're structural engineers, we're just a small part of the bigger picture. The success and the accolades for the line-wide design, we're very much indebted to our colleagues across those other design organizations who had, first of all, the very well-conceived vision to start off with, but there are multiple individuals I can think of who had that design talent to come up with that initial vision, but also the tenacity and the drive to see that through, the incredibly long timescales that you get with a major infrastructure project like this. We're talking 14 years in total from the outset to completion. Secondly, I think I like to think what we did as the line-wide design team embodies the adage that it takes more work to keep things simple. That the end impression of the subsurface rail is very uncluttered, clear, and simple. But hopefully, as I've given you a taster of in these slides, that underneath that there was a lot of work, a lot of technical challenge in order to make the end result appear clear and simple. Thirdly, I think the common components package concept is maybe underused on large infrastructure projects or even large building projects. The idea of client design teams looking to rationalize early on, taking the bigger picture and trying to identify those repeating components that will be deployed, throughout an infrastructure network, a transportation network, and getting those economies of scale by pre-designing them, pre-engineering them up front so that they can then be passed on to multiple package contractors, I think has been another key success of the delivery we had on the Elizabeth Line. And then a final one here, again, it's a bit of a soapbox of mine, but indulge me for a second. I just see that as a profession, sometimes we have a little bit of a reflex to look at sort of secondary structures and quickly sort of kick them away. That's by others. If you look at what we designed for the PES frame, there wasn't a single element longer than about 3 meters. There wasn't a cross section deeper than 200 mil. I don't think there was a connection force greater than about 20 kilonewtons. In terms of order of magnitude and scale, it's small fry, but in terms of engineering complexity, it absolutely wasn't small fry. And I just would like to just put that out there to my structural engineering colleagues, just to encourage you to sort of look again at the the possibilities that exist in those secondary structures. Once you've got the main frame up, once you've got the tunnel lining constructed, what else is there that you could be engineering and applying your ingenuity to, which could add significant value? So on that note, I will end. Thank you.